Welcome everyone to today's webinar with CWNP. My name is Tom Carpenter. I'm the CTO at CWNP, and I'm glad to have you here with me today. We are going to talk about a couple of those IoT protocols that are common for wireless industrial deployments. And these protocols, I'm discussing them together because they are very, very similar. And so as we go through the process today, what I'm going to do is talk about WirelessHART first in general and then get into specifics. And then there are some things that overlap somewhat between WirelessHART and ISA100.11a. And so I'll talk about those as we transition over to ISA100.11a, so we don't have to talk about them twice. So we'll cover WirelessHART and its uniques, then the things that are shared between them, and then ISA100.11a and its uniques. Now this material is some of the material that you would need to know for the CWICP certification exam, just so you know if you're curious about that. And there is a chapter on these two protocols in our study guide. And of course, they are two of the, if memory serves me right, 10 protocols that are covered in the CWICP certification. So that certification actually covers 802.15.4, which is the foundation of these two protocols, by the way. So that's very important to keep in mind. I'm not going to go into details about 802.15.4 today. Maybe at another time we can do that. But know that these two protocols are based on IEEE 802.15.4, and they specify the portions of that standard that are to be used, and then some customizations to it as well. So we also cover other protocols: Bluetooth, Zigbee, Z-Wave, Sigfox, LoRaWAN, on and on the list goes of other protocols covered in CWICP. Basically, through research, we determined the 10 most commonly used protocols and focused on those because there are literally, even if you don't get into the proprietary protocols, 25 to 30 protocols used within the space. And so the good news is when you understand the ones we cover, it's very, very easy to quickly get up to speed on any unique protocol that you might need to understand as well. Of course, we're on Twitter at CWNP and at Carpenter Tom, and this webinar, as all others, will be archived on the YouTube channel on CWNP TV. So you can always go there to review it, or if you've missed a webinar in the past, the archive is there, plus videos from our past conferences. Okay, with that said, let's take a look at WirelessHART and ISA100.11a. Now, as I've already said, both protocols are based on 802.15.4, and they do operate in the 2.4 gigahertz band. Now, at first, that might seem like a problematic thing, and of course, it's more problematic than operating in some other bands, but they do use a channel hopping technique that does allow for some resiliency. And they use narrow enough channels that significant frequency spaces that are used by Wi-Fi, for example, can be avoided to a certain extent. Now, obviously, if you get WirelessHART or ISA100.11a in an environment that also has Zigbee, that also has Wi-Fi, that also has Bluetooth, that also has proprietary stuff using 2.4 gigahertz, yes, you're going to run into challenges. So that is reality. It is the 2.4 gigahertz band, and that's the reality of living there. But this protocol is very robust for several reasons, as you'll see as we go along. Now, only portions of 802.15.4 are implemented. It uses the OQPSK PHY out of 802.15.4, and it doesn't use any of the other PHYs. It does not use any of the other capabilities other than those explicitly specified in the WirelessHART or the ISA100.11a standards. They do extend it, so they make some tweaks or changes. Even though there might be something referenced in 802.15.4, it doesn't mean it's implemented in exactly the same way in WirelessHART and ISA100.11a, particularly if it's something that can be controlled above the chip level. So let's get an overview of WirelessHART. First of all, it's compatible with the HART application layer. So HART is the Highway Addressable Remote Transducer Protocol. And this is a wireline protocol. It's been used since really the 1980s in industrial environments and other environments as well. HART is a very simple protocol. HART is very reliable for some unique reasons that we'll get into. One of the key things about HART, the wireline protocol, when doing FSK, PSK, RS485, as you see in the graphic here, is that it is a continuous current protocol. So there's always some current on the wire. And because of that, if there's ever no current on the wire, we know there's a failure. So there can be this immediate awareness of failure. You don't have to wait for a packet to not get through or something like that. It's just that if the current is not there, then the connection is not there. And so it fluctuates between two current levels for signaling purposes, and very simple, very easy to use. And that's down there at the PHY layer, of course. The HART application layer, the commands for HART are the same commands that are used in WirelessHART. So that application layer is supported. And that means it works with existing HART developed applications as long as they don't do something odd and actually care about the physical layer or the MAC layer. It also has support for multiple devices from different manufacturers, so it's not locked into a particular vendor. This is not some kind of a proprietary solution like maybe something from Monet Networks, for example, where they have their own proprietary protocol. They're good devices, but they use proprietary solutions, so you're locked into that manufacturer. It does target unit level process operations, and this means equipment and process monitoring, managing assets, predictive maintenance. If it's non-critical control, that's the primary target. The reason WirelessHART obviously is not aimed at critical control is, well, twofold. One, it's wireless in general. Two, it's wireless in 2.4 gigahertz. So critical control means, you know, life is in danger, significant financial loss danger, these types of things that demand that a message get through. That's the big thing. And so there are several different possible applications for this. I would suggest, if you want to maybe look for some case studies, things like that related to WirelessHART and ISA100.11a, take a look at Control Engineering. It's a magazine. It's completely free to subscribe to the digital edition of. And if you search for Control Engineering, that's CONTROL, Control Engineering, you'll find not only that you can subscribe to it, but you can go into the PDFs of all of the old past issues of the magazine. So you can go and dig up old articles on LoRaWAN, old articles on ISA100.11a, or anything else like that that you might want to look at. So it's very, very useful. I always encourage people to take a look at that particular free magazine. Now, WirelessHART uses 802.15.4. Depending on where you look in the specification, sometimes it says 2006, sometimes it says 2011. And the most recent specification is based on 2011, but you might have an older device that's actually based on 2006. It shouldn't cause any significant communication problems in most cases, because the changes do not have a massive impact. That is, a 2006 device can still communicate with a 2011 device using OQPSK. So in most cases, you're okay, but you always want to test if you do have old devices like that. WirelessHART specifies the requirements directly from 802.15.4. It provides tables listing exactly what's required, and it also defines management parameters used to control that PHY. It specifies the requirements of the PHY to make sure that there's interoperability among all the different HART devices. And it does implement a mesh topology. And so what that means is that there are redundant routes through the network to the eventual network manager, gateway, security manager, all the components that make WirelessHART actually work. So what are those components? Well, first of all, let's start with the end devices. They're called field devices in WirelessHART. And this is either a device that has a WirelessHART gateway, or I'm sorry, WirelessHART radio built into it, or it might be a HART wireline device, an older HART device. And then what you do is, instead of plugging that HART device into the HART network, the wired network, you connect it to a WirelessHART adapter. So the second thing listed here, the adapter, is the thing that lets a wired field device connect to the WirelessHART network. Now, depending on how you look at the understanding of the language in the specification, you could say that even WirelessHART devices have the adapter. So the adapter is a module, it's a component on the WirelessHART device. But certainly an adapter can be used to connect a HART device to the WirelessHART network. Then you have the network access point, a familiar device name for those that work in the Wi-Fi world. And this is a device that connects the gateway to the WirelessHART network though. So basically your gateway may not be wireless at all. The WirelessHART gateway may be a wired only device. And the access point is a separate device that connects to the gateway as well as connecting field devices. However, you can get gateways that are all in one. I mean, you can get a single device that is your gateway, your network manager, your security manager, your access point, everything all in one. But they can be completely separate components. Then you have the gateway device itself, which is the thing that is going to provide connectivity to the plant automation network or a host network for the WirelessHART network. So it's basically the thing that gets those field devices connected to something, right? It's either going to connect to a plant network, it's going to connect to just your regular network. It just depends on what you're implementing in the control and security of it. Then you have the router device. A router device is basically a repeater. It's a device that can route WirelessHART messages. It may not be connected directly to a field device. So a field device might connect to one router, which connects to another router, and so forth. And then you have your handheld devices. These handheld devices are used to join the field device, basically to get them onto the network. You have the security manager, which manages the security encryption keys for your field devices. Then you have the plant automation network, which is the network that eventually connects to your plant automation application or host application, your plant automation controller, whatever it is that you want these field devices to talk to. Okay, so you can think of this almost like, if you're familiar with PLCs and RTUs and things like that, then you can think of this like the PLC is on the network and my WirelessHART field device needs to have some way for communications to happen between it and the PLC. So if you think of it in that way, it's a similar thing. It's just that WirelessHART is the protocol we're using for the field device to communicate eventually with the access point through the gateway to the plant automation controller. Now, we may also have a process automation controller, and this is a thing that allows you to integrate with SCADA or DCS systems directly, so you can connect the two types of systems together. Now, our WirelessHART devices then, we see here an example from Nexcom of an all-in-one gateway, network manager, security manager, and access point, all of it, and then it's got either Wi-Fi or Ethernet for the backhaul. So whichever you want to use, you can connect to your plant network in that way. And then on the right, we see a field device. And so you can see that it's a WirelessHART device, and we can see the wireless radio on it and so forth. Field devices come in all shapes and sizes. They basically are connected to equipment to monitor equipment, possibly connected with multiple sensors to do sensing of whatever the type is: pressure sensing, motion sensing, light sensing, temperature sensing, any number of other things, right? So they're just connected to some system that allows them to monitor metrics from it and send that telemetry data back. And it just happens to be that these devices are using wireless in the 2.4 gigahertz band based on the 802.15.4 PHY to send that data across the network. So what are the required features of 802.15.4? Well, there are several things specified in 802.15.4 that not every 802.15.4 device uses, right? WirelessHART says these are the things that the chipset has to support to work with WirelessHART. We need RF power measurement, and basically this is a measurement of the RF power where the transceiver connects to the antenna at the antenna connection. So it needs to be able to measure that. It needs to control transmit power. And basically the WirelessHART compliant devices are going to define their transmit power through the PHY transmit power parameter, and it's going to be based on regulatory constraints, things like that. Receiver sensitivity definitions have to be there. The receiver sensitivity is defined in 802.15.4 itself, and it's based on the input signal with a packet error rate of less than 1%. So what is the signal when the packet error rate is less than 1%? And the PSDU length is 20 octets long. So in other words, I can get a PSDU that's 20 octets long through with less than 1% packet error rate. Whatever the signal level is that I can do that at, that's my receiver sensitivity. So that's how it's defined in 802.15.4. And therefore, that's required of WirelessHART. And then that gives you something as a metric. As you know, if you've studied Wi-Fi, it gives you something as a metric that you can use to calculate the range of your links and what kind of signal you need in your environment for the system to work. We also have PPDU format specified based on 802.15.4. And the example that you see here of the PPDU format, very, very basic. We have a sync header, a PHY header, and the PHY payload. So the PHY payload is the PSDU, the upper layer data coming down from the data link layer. And then the PHY header is that which is unique to the PHY. And we have the frame length and 1 bit that's just reserved at this point. And then for the sync header, it's just a preamble to indicate that a message is coming through, and then a starter frame delimiter. The 2.4 gigahertz specs are what we're using, and we're using particularly the OQPSK modulation, or physical layer, I should say. The modulation is DSSS. We have also defined transmit to receive and receive to transmit turnaround time. So in other words, this is what is the time in which the radio must be able to switch between transmit and receive. And the specification requires a turnaround time which is 12 symbols long, which comes out to about 192 microseconds. So we've got to be able to switch the radio in that amount of time for it to be compliant with what WirelessHART desires. And then we have energy detect and clear channel assessment. Now this is one that's a little bit different within WirelessHART. Energy detect, of course, is a method used to detect the received signal power in the channel. So we're detecting the actual energy that is there. And then the clear channel assessment is part of that operation. Now, energy detect is used in clear channel assessment with 3 modes within 802.15.4 and WirelessHART. Mode 1 is just energy detect. Mode 2 is carrier sense. And mode 3 is carrier sense and energy detect. Now the difference between them is that energy detect doesn't look at the format of the signal. It doesn't look at what the signal is. It just sees energy at a certain power level. Whereas carrier sense does. And basically carrier sense only recognizes signals that are based on 802.15.4 as a specification. Now, what you have to use is a little bit flexible and different between WirelessHART and ISA100.11a. So time allowing, I'll talk a little bit more about that later on. And then we have the link quality indicator, which is basically just a measurement of the quality. It's implemented based on using the energy detect, the signal to noise ratio estimation, or both. And so it is just a measurement that is passed up to the higher layers saying what the link quality is. Now it is important to know that while not listed here, WirelessHART uses channels 11 through 15, but it does not use channel 26. Now that'll come into play more a little bit later on. I'm sorry, channels 11 through 25, but it does not use channel 26. And that'll come into play a little later on. We talk about ISA100.11a. So WirelessHART, no channel 26. Very important to remember. And we actually see that visually represented here. So channel 11 is center frequency 2.405 gigahertz through channel 25, center frequency 2.475 gigahertz. As you can see, there is 5 megahertz of space between each channel. So we go from 405 to 410 to 415 and so forth, marching right up through. Remember, channel 26 is not supported in WirelessHART. The radio turn-on time is less than 4 milliseconds, and it must be capable of transmit power in the range of minus 10 dBm to 10 dBm, with 10 dBm being the default according to the specification. And the sensitivity needs to be minus 85 dBm or better. Okay? So how do we actually transmit in WirelessHART? Now that we have all those fun, hard specs out of the way. And by the way, remember, this is being recorded, so you can review this material again on CWNP TV on the YouTube channel. So the first thing we do is we turn on the transceiver, which remember has to happen within 4 milliseconds. We perform a clear channel assessment. Then if the channel's clear, we begin our transmission. And then the PHY, and we're beginning the transmission, of course, at the data link layer. And then the PHY layer receives that request, and we send the packet. Now, notice that if we're transmitting it, beginning at the data link layer, and then of course the physical layer actually sends it. So it starts on the left at the data link layer, moves through the middle of the physical layer, and then the receiver receives it and sends an indicator up to the data link layer. And the data link layer receives the packet and does error checking. And of course, if there is an error, then it can discard the packet. So you can see the basic flow. It's a pretty simple flow for how this works. The things in this diagram that are important to know, the enable.request, the enable.confirm, all of those are primitives within that layer. So the data link layer has an enable.request, which communicates with the physical layer, and the enable.confirm comes back from the physical layer saying, hey, we're good. And then notice there's a CCA request and a CCA confirm. The confirm comes back and says, yeah, the channel's clear. And so then it says, okay, then I've got a request for you to send this data. The PHY layer sends it, and then after sending it, sends back a confirm that the message was sent. So these are, again, primitives within the data link layer. And a primitive is simply, you can think of it as a minimum required function or capability within the layer. Okay. And then, of course, on the receiving side, basically, we're going to say, hey, any packets coming in? Yes, there is. All right, give me the data. All right, here's the data. And then you can see that we have our actual data received, or possibly an error if there was packet corruption in the transmission. So here's the MAC frame format, because I know we all love MAC frame formats. Now the MAC frame is very similar to 802.15.4. In fact, the sequence number, network ID, and destination and source address fields are all basically just the 802.15.4 fields. Now this is an 802.15.4 MAC frame, but WirelessHART does some creative things with it. So it takes that first byte and it says, all right, this first byte, 8 bits, is always going to be 0x41 in hex. And so this indicates it's an 802.15.4 data frame with security enabled. The second byte, and by the way, this second byte called the address specifier here is the last 8 bits of the 802.15.4 frame type field. So in 802.15.4, these entire first 16 bits or 2 bytes or 2 octets are the frame type field. But WirelessHART says we're going to take that second half and use it for a specific purpose, the address specifier. And you see the address specifier pulled out in the bottom of the slide here. And basically what we're going to do is if bit 3, or actually I'm sorry, bit 2, if bit 2 is a 1, then it's an EUI64 address. If it's a 0, then it uses a nickname, it's called within the standard. And then the same thing is true for bit 6. If bit 6 is 1, it's an EUI64. If it's 0, it's a nickname. So basically, bits 2 and 3 are both equal to 1 when it's an EUI64 destination address. But if it's a nickname, then bit 4 or rather bit 3 is a 1 and bit 2 is a 0. The one that's just shaded here is bit 2. Remember, we start at bit 0, right? So that always gets confusing even to the explainer to remember what bit order you're talking about. And so there are 8 bits, but they're numbered 0 through 8. So that second byte is used just to define what the later destination or source address fields will be. And so that's why you'll notice for them, they are 2 or 8 bytes, because it depends on whether I'm using a nickname or a full EUI64 address. Okay, so 8 bytes. What is 8 times 8? There you go, right? So if it's 8 bytes, that's because I'm using the EUI64. So that second octet is communicating to the receiver how big the destination address and source address fields are going to be. And that's what it's used for. So again, a little tweaking to the 802.15.4 specifically for use here in WirelessHART. And then of course you have your payload, and you have a message integrity check and a CRC. So all of that is there. We also have a DLPDU specifier that's 1 byte right before the payload. This is used to indicate the type of DLPDU. Now, DLPDU is a data link PDU, protocol data unit. Okay, and so basically, it's the thing that we're creating here, and so the type could be an advertisement, a keep alive, disconnect notice, or it could be data. So if this byte uses bits 0 to 2 as all ones, then it's a data. If 0 to 2 is 110, it's a disconnect, for example, and so forth. So basically bits 0, 1, and 2 are used to specify the type. And bit 3 indicates the type of network key that's going to be used. So there's several different things that are defined in this 1 byte. We can also indicate the priority of the DLPDU. So it can be an alarm, a normal priority, a process data priority, or a command, which is the highest priority. So the lowest priority is an alarm, oddly enough as that sounds, and the highest priority is a command. So the lowest priority for bits 4 and 5 would be 0, 0, through to the highest priority being 1, 1. Okay, so this is the basic frame format. If you've looked at frame formats before, you get these concepts, and they're fairly simple to understand. It's a fairly simple frame format, particularly if you compare it to the latest and greatest updates to the 802.11 frame format. Now, I said one of the things that happens in WirelessHART is channel hopping. And so indeed, it is going to do channel hopping. Now, this is our transition period. This is where we're going to start to transition over to eventually just talking about WirelessHART, but we have a couple things to talk about here that both of them use. So both WirelessHART and ISA100.11a use channel hopping. And channel hopping is just what it sounds like. Use one channel, then move to the next, then move to the next, then move to the next, right? So channel hopping, I'm hopping around on different channels. Now, this hopping takes place across these channels in a defined pattern. So there's coordination that happens between the devices within the WirelessHART network. Channel hopping basically says, hey, while we're on a channel, use OQPSK with DSS modulation to transmit, and then hop to the next channel to transmit and so forth, or to receive. Now, while WirelessHART supports only slotted channel hopping, which you see illustrated on the right, ISA100.11a supports slow channel hopping. So a different kind of channel hopping. This is a key differentiator between the two protocols, but I do want to point out that the phrase slow hopping in the IoT protocol literature that's out there is often just used to refer to any hopping similar to what is used in ISA100.11a and WirelessHART, but within the standards, only ISA100.11a between these two actually supports slow hopping. So slotted channel hopping simply means that one slot time is used on a channel, and then the next slot time hops to another channel. So we hop for each slot. Slotted hopping. Slow channel hopping means the device can dwell on a channel for some period of time, say 250 milliseconds, before hopping to the next channel. And then hybrid channel hopping is implemented when it is such that a device uses a slot and then dwells on the channel for a period of time before hopping to the next channel. So basically it only uses one slot, but it stays there for a period of time, possibly to hear transmissions that might be coming in. So channel hopping is a little different between slotted and slow. The big difference is, remember, slow hopping means I dwell on the channel for longer than a single slot time, longer than just enough to send one communication, right? I'm going to stay there for more than a slot time, up to 250 milliseconds. The channel hopping pattern, the sequence, they're considered pseudo-random. ISA100.11a defines two parameters, a predefined hopping pattern and a hopping pattern offset value. So there's a predefined hopping pattern. Let's say you choose hopping pattern A, and then there's an offset value. So, okay, that's the normal hopping pattern, but here's how I want you to vary it. Okay, so it defines both of those different parameters to make adjustments to the hopping patterns. The predefined hopping patterns are designed basically so that each incremental hop will not overlap with the same 802.11 channel, 1, 6, and 11. They're actually strategically designed that way so that they avoid causing any more interference than necessary with Wi-Fi. So for example, when we deal with the channels, you see channel 11 through 26 in the graphic at the bottom of the slide here. 11, 12, 13, 14 are in channel 1. 16, 17, 18, 19 are in channel 6. 21, 22, 23, 24 are in channel 11. 15 and 20 and 25 and 26 kind of sit outside the boundaries of channels 1, 6, and 11, right? Well, notice the first hopping pattern defined for use with a ISA100.11a is, let's start on 19. That's in channel 6. Then go to 12. That's in channel 1. Then go to 20. That's between 6 and 11. Then go to 24. That's in channel 11, and so forth. So notice how we're not just hopping 11, 12, 13, 14, because then we're going to dwell for 4 slot times, or possibly 250 milliseconds times 4, all in channel 1, right? And so to avoid that, we have hopping patterns that jump around. Now, that sounds really good at first, but then when you think about it again, it basically means we're hopping all over the spectrum. So the reality is that even with measures that are put in place algorithmically and so forth to try to help avoid interference with Wi-Fi, or from Wi-Fi for that matter, there is still a reality of the possibility of interference. Now, WirelessHART, unlike ISA100.11a, does not specify the patterns and defaults to just using a sequential pattern, but it does implement a channel offset, and therefore multiple devices can communicate in the same slot if they have a different channel offset. So basically, it's important to know that WirelessHART defaults to sequential, but there are offset parameters that can be specified that adjust that. Additionally, I should note that there's a feature called blacklisting that can be used if supported, and basically that just says don't ever use the following channels. For example, I mean, if you could get by with just using 15, 20, 25, 26 in ISA100.11a, or 15, 20, and 25 WirelessHART, then you could say don't use 11, 12, 13, 14, 16, 17, 18, 19, 21, 22, 23, 24. So you could basically say don't use those channels and use the others. Now that would be a very odd implementation, but it's what blacklisting theoretically could do, but your system would have to, of course, support blacklisting. Now, the next thing that is shared between the two before we move on to just talking about ISA100.11a is superframes. All right, when I talk about superframes, I always like to start by saying one very important thing. Superframes are not frames. Superframes are not frames, at least not in the traditional sense of a MAC layer frame, right? A data link frame. Superframes are better thought of as windows of time, okay? But they are scheduled windows of time associated with a channel. So there's Superframe A for this time on channel 11, Superframe B for this time on channel 24. Okay, so superframes are boundaries of time. The frame is wrapping around a time boundary that contain slots. Okay, and those slots can be assigned to devices for them to communicate. Now, I want to show you when I say there's similarity between ISA100.11a and WirelessHART, I'm not overstating anything. There is tremendous similarity. In fact, the graphic at the top is a screenshot from the WirelessHART spec. The graphic at the bottom, on the left, is a screenshot from the ISA100.11a standard. Do you notice, not only are they similar, literally the dark lines going across the top and the bottom both just happen to have rounded ends on them. It's just in ISA100.11a, they're shaded in blue, and then the text inside is a little different, and WirelessHART adds this extra cycle n plus 1, n plus 2, and so forth nomenclature. So the graphics are so similar, it makes you think they either looked at each other or they literally used the same base graphic to build it out. Now, as you can see in the images then, they are very, very similar, and both have, for example, device A to B, B to C, and so forth. So what that means, by the way, is device A communicates with device B in time slot 0, B communicates with C in time slot 1, and then time slot 2 is undefined. Then A communicates with B in time slot 0 in the next frame, or slot rather, and then in time slot 1, B communicates with C, and then in time slot 2 it's unassigned. Now those unassigned don't mean they won't be used, it just means that they're not restrained for use to those assigned devices. Okay, and so you can see then that there's a lot of similarity between the way the two define this. Now it is important to know a couple of things. Basically, no communications are scheduled in the network without a time slot being assigned. Every new Superframe instance in time is called a Superframe cycle, by the way. And so that's just terminology from within WirelessHART. But ISA100.11a simply uses the phrase cycle or Superframe cycle in relation to the concept without any kind of direct declaration that that's what it is. So they use similar terminology like that. Here's the big thing. All transmissions in WirelessHART and ISA100.11a use Superframe schedules. Slots within the Superframe can be dedicated or shared, as we've seen, but generally dedicated indicates that a pair of devices have the slot and no other device can transmit in the slot. However, ISA100.11a does allow the dedicated slot to be shared, but it's still referenced as dedicated because exponential backoff times are not used when retries are required. So in other words, two can compete, but then they don't have to do any type of special backoff if they need to retransmit. Shared slots have to use exponential backoff times when required in both ISA100.11a and WirelessHART. Okay, so that's important to know. Now, two things about superframes. Again, they're not frames, and the duration of time slots times the number of time slots in a superframe determines how often a device can communicate. So if each time slot is 100 milliseconds and the superframe has 5 time slots, the end result is that each device participating in that superframe will be able to communicate every 500 milliseconds, once each cycle, assuming that the time slots are assigned to 5 different device pairs. So it is important to know that you have some really solid control over who talks when within these networks because of the use of superframes. Now, how the superframe management is actually implemented within the devices that you deploy and use is going to vary. So that's one key thing to look at when you're selecting vendor solutions in this space, is how they give control to the administrator over superframe management. And by the way, just generically, since I've used the term a lot, a time slot is the amount of time required to send or receive one frame and an accompanying acknowledgement, including all time gaps that may be required between frames. So how long is a time slot? It's the amount of time required to send or receive one frame and an acknowledgement. That's how long a time slot is. And you can, of course, look at the spec, calculate any kind of microseconds that you might want to calculate or something. But a time slot always allows at least a frame and an acknowledgement if no collision occurs, because it's a shared slot, for example. So 802.15.4 frames are never any larger than 127 bytes. Therefore, a time slot is enough time to send 127 bytes in an acknowledgement. It's really that simple. All right, so now let's talk about ISA100.11a. The goal of this protocol, similar really to WirelessHART, but with a little more control, is monitoring, alerting, supervisory control, open loop control, and closed loop control. Basically, this is some common terminology in the industrial space. If you're not familiar with that, just keep watching. We'll be doing more webinars. I've already had requests come in. We talked a little bit about industrial terminology. We've done some blogs about it. So we're going to get into some of these concepts in more depth later on. It's not important now to understand ISA100.11a itself, but it is important to know that it can be used for some of these things like closed loop and open loop control. The application focuses on performance needs of process automation, monitoring, and control, and to work in industrial environments. It is aimed at meeting usage classes 1 through 5, which excludes emergency action. So explicitly, it states in the standard that it does not have intention of being used for emergency action, just 1 through 5, which is basically regulatory control, supervisory control of closed and open loops, alerting, and logging. Now, does it use 802.15.4? It sure does. And we see here the data link layer specified by the standard includes a subset of 802.15.4. This handles the low-level mechanics of sending and receiving individual DPDUs, all of which are classified as data DPDUs. So in other words, we're only sending data 802.15.4 frames with ISA100.11a. There's also an extension to the MAC, including aspects of the data link layer that are not specified in 802.15.4. And there's an upper data link layer protocol. So one of the key things that ISA100.11a does to give even better control and management of the network is that it actually has what they call an upper data link layer protocol. So it takes the MAC and says, all right, we're going to do what 802.15.4 does, at least the parts that we require, but we're also going to do more than that. Okay, so it has this concept of an upper data link protocol that it implements. The network components, similar in terminology, we have a field device. These field devices can be in an I/O role, a portable provisioning device, or a routing role device. So the I/O role is the device that you typically think of as the end device, right? It's the thing that you want to deploy. The portable device is a device that provides for provisioning, usually some kind of handheld device that you go around to provision the field devices with, the other field devices. And then there's a routing device, also considered a field device. And this is really aimed at just routing so that the end field devices, the I/O field devices, can get through to the backbone router and or the gateway. So those are field devices, but then we also have infrastructure devices defined. There's a backbone router. It's a device that can route between ISA100.11a networks and other networks, possibly to a gateway. Basically, this is all based on IPv6. So you're using IPv6 for these operations with ISA100.11a. That's important to know. We also have a gateway, and this is a device that can connect to a plant network, right? We have the system manager and the security manager. The system manager manages the network. It controls all those superframes and things like that, right? And then the security manager is the thing that manages the keys and the joining of the network and so forth. And then, of course, you have a plant network. And the plant network is the network that connects your ISA100.11a network to possibly eventually a control system, maybe integrating with a SCADA system or something like that, okay? A lot of details here. Remember, this is being recorded. It'll be on YouTube. You can pause it, stare at the screen as long as you want. Now, required features of 802.15.4. Again, OQPSK. with the DSSS modulation in 2.4 gigahertz, has the supported 250 kilobits per second data rate, which is what that PHY supports. The channel change time, less than 200 microseconds, so it has to be able to switch during channel hopping within 200 microseconds. The turnaround time is 200 microseconds for TX to RX and RX to TX2. CSMA-CA is optional based on regulatory considerations. In other words, you can just talk, right? It is optional. When used, it's most commonly implemented with CCA Mode 1 that we talked about earlier. Channel 26 is optional but available. So unlike WirelessHART that says it's not available, it is optionally available here, but it is optional. The minimum transmission power here is -3 dBm instead of -10. And the maximum transmit level power simply cannot exceed regulatory requirements. They don't really put a top constraint on that within ISA100.11a like they do in WirelessHART. Now, what's the communication procedure look like? Well, remember, we've got the I/O device, the routing device, the gateway, and a control system to think of, right? So basically, we're going to communicate from the I/O device through the routing device to the gateway. And notice the key here is that the routing device only ever de-encapsulates up to the data link layer. It doesn't care about the rest of it. But the gateway is going to have to de-encapsulate all the way up to the application layer. And then, of course, it can forward it on through the plant network to a control system or something of that sort. So we're using the ISA100.11a protocol between the I/O device and the routing device, and between the routing device and the gateway, generally speaking. It is possible that we could be connecting from the routing device to the gateway through a wired connection instead. But more often than not, it's wireless. So this is the basic communication flow. Here's the MAC frame format. I'm not going to spend as much time on this one as we did the WirelessHART. But notice we do have 2 octets for the frame control. And then we have a sequence number and addressing fields. Then we have an auxiliary security header. So this is the new part, you might say, for the actual ISA100.11a, is we're using that auxiliary security header that is specified in 802.15.4. Then we have the data payload and the frame check sequence. So the basic concept here is that we're going to have a PHY header eventually. It's called PHL in the lower portion of this diagram. A data link header, which is basically your frame control, sequence number, addressing fields. A network layer header, that's going to be in the payload of the frame up above. A transport layer header, also in the payload of the frame up above. And an application header for the application PDU, which is again going to be in the frame up above. So ISA100.11a specifies all these different layers and how they're used. But it's important to know the network layer that it specifies is IPv6. So ISA100.11a and 6LoWPAN. ISA100.11a uses 6LoWPAN for the network layer. So 6LoWPAN, if you look at that standard, and we have an entire chapter on 6LoWPAN in the book, and it's also part of the certification, CWICP. 6LoWPAN is an RFC specification by the Internet Engineering Task Force that specifies the use of 802.15.4. Okay, so the reason, part of the reason why ISA100.11a uses 802.15.4 is because it specifies 6LoWPAN for IPv6 operations, which in turn specifies the use of 802.15.4. So we do have the implementation of RFC 6282 compression format for IPv6 datagrams. So this is about header compression. When we say compression here, we're not compressing the payload. So we're not using, zip or RAR or something like that. We're compressing the headers, not with any type of compression like zip or RAR. We're compressing by saying we can take stuff out we know we don't need, or we can represent stuff with fewer bits. But it's based on RFC 6282. Each device has an IPv6 address, a link local address. A 16-bit address is also used on the local subnet to convert energy. In other words, we don't need that 16-bit address everywhere, right? We can do less data processing and save energy in possibly battery-powered devices or something like that. And then all devices maintain a table that translates the 16-bit address to the IPv6 address. And that's why we can communicate on the local subnet without needing the 64-bit address, but anywhere we get to, that nickname, that 16-bit address, can be translated to 64-bit address when we do need to actually use its IPv6 address. Security in both WirelessHART and ISA100.11a is provided by the fact that we have provisioning. So you can't just talk on the network, you've got to be provisioned onto the network and then joined to the network, which gets you your keys, which establishes the network ID and so forth for communications. And then once we're connected, we have message integrity and confidentiality through cryptographic algorithms because of the fact that we were securely joined to the network. Now there are different elements. You can have a pre-installed symmetric key so the device can immediately join for basically out-of-band provisioning. We can use a network ID with a join key to join. We can join with handheld devices like the one that we see in the image here to join a device to the network and provision it for operations. All right, so let's summarize with a comparison between these two. WirelessHART and ISA100.11a. They both work in 2.4 gigahertz. They both use OQPSK with DSSS. Therefore, they have 250 kilobits per second data rate. So notice this is not like Wi-Fi, if you're familiar with Wi-Fi, where we have, what is it? I believe, if I'm not mistaken, it's now 3,749,693,432 different data rates. That's a bit of an exaggeration, but we do have a lot of different data rates there. And of course, that's because we want them. We want it to be faster if we can go faster, slower if we have to go slower, and so forth. But here we don't need fast data rates. This is not intended to send 10 megabyte files or 10 gigabyte files. This is intended for small communications, right? 250 kilobits per second is plenty. And that's another reason why it can still be resilient and function well within 2.4 gigahertz. Channelization, WirelessHART is slotted hopping only and only uses channels 11 through 25. ISA100.11a is slotted or slow or hybrid, and it uses 11 through 26, but remember 26 is optional, so check with the vendor specifications to see if it's supported. They both use AES 128-bit encryption. WirelessHART requires backoffs on retries. With ISA100.11a, it's optional, because remember, it might not be a shared time slot. Clear channel assessment is required by WirelessHART. It's optional in ISA100.11a as a specification, but the regulatory domain may require it for the radio to be able to be authorized for use in that domain. So those are some differences between the two. All right, that's the scheduled content that gives you an overview and sometimes deep dive into the underneath of WirelessHART and ISA100.11a.